Well, welcome back. So after we've spent quite a bit of time now working on techniques for integration, finding antiderivatives, etc., there's just going to be some times when we can't apply any of those to, to evaluate a definite integral. For example, there are just some expressions that we don't know the antiderivative of. There is no known antiderivative. In which case, if I wanted to evaluate a definite integral, we wouldn't be able to do it with the fundamental theorem of calculus. Hence the need for approximation methods to estimate these values. And so the topic today is to learn a couple, or review a couple, and to learn a couple of new ones, methods to approximate the values of definite integrals. The warm-up for today's lesson is just to try this area problem, finding the area of this trapezoid. Now, there are a number of ways to do this one. Maybe some of you see that we could break this up into a rectangle and a triangle simply by dividing across like this and creating a triangle and a rectangle. But I'm going to suggest another way today, and that is to simply divide it into two triangles by cutting a diagonal right here. The reason I'm going to do that is because then I can use the number 2 twice, and I'm going to have the same shape both times. So the area of the first triangle, the one down here, this is going to be a right triangle. So you could call the base 3 and the height 2, or the base 2 and the height 3. It really doesn't matter. It's going to be 1/2 multiplied by 3 and 2. Now let's take a look at the second triangle here, and this time there's the long edge 5, and if you kind of see what you might call the height of this triangle from the point here straight down to this length, that's going to be also 2. So I would say this is 1/2 of 5 and 2. Now, if all we wanted was the answer, we'd go ahead and compute this. But I would like to instead examine this a little closer and see another way to rearrange this expression. Notice that both terms have the 1/2 because it's in the formula for a triangle. And they both had the same, both these triangles had the same distance from side to side. They both had the 2. And so I would like to cleverly remove 1/2 as a common factor and put it on the right. I would like to kind of remove the 2 kind of as the quote-unquote height of the triangles and put it over here. And then the 3 and the 5 add together. If I were to rearrange it one more time, I can kind of write it like this. Now we know that for a rectangle, the area is simply the base times the height, or the length times the width. Now in this trapezoid, you could call the 2 the width. And the way I like to see it now is I'm using the 3 and the 5, and I am really, do you see how I'm adding and dividing by 2? So I'm really finding the average of the 2 lengths here, the 3 and the 5. So it's kind of like we're finding the average height of the trapezoid and multiplying it by the width. I'm going to kind of write that here. So in that way, it's almost like this is a general way to solve all shapes where there's 2 parallel sides. If it's a rectangle, these 2 lengths are the same, and so you just take that times the width. If they're different, you just take the average of the 2 and multiply it by the width, and that's how this trapezoid actually works. And we're going to make use of that method today in our calculus lesson. Now our topic is numerically approximating integrals, definite integrals. A couple of ways, a couple of reasons why you would have to do this. First, maybe the expression you have here maybe the integrand of your function, there's no known antiderivative, or at the very least, the method for solving it, the method for finding it is one you haven't learned, then this would be a reason why you might have to just estimate the answer. Or second, maybe you don't even know the formula for this integrand. Maybe you're trying to estimate area under a curve, but the curve's equation is not known. Maybe just a few sample points are known, in which case you would have to have some way to estimate the integral value. Well, let's revisit some methods we've learned prior to today. They all involved dividing an area under a curve into rectangles. Okay, so I've got a graph of a curve here. I wish to find the area from a number A to a number B, and we could even divide this region in like this. And so in 3 different techniques for using rectangles, one would be to take maybe my first subinterval, take the leftmost point on it, and just draw a rectangle straight across. And I could do that the entire way across, but this would be an example of a left-sided rectangle. And if I did this the entire way across, I would call this a left Riemann sum. And notice that the width of these rectangles is some distance delta x, and the height of this rectangle is a function value, f of, I'm going to call it x sub I, because these indices here is going to help us count the fx values along these subintervals here. And so basically, basic geometry, base times height gives us the area of that rectangle. Now, suppose in a different situation, I would like to measure the rectangle on the rightmost point. So in which case, maybe this next subinterval, I'll pick the rightmost point and measure the height there. And if I did that all the way across, that would be what's called a right Riemann sum. But again, the width is the change of x between these 2 points, and the height of the rectangle is simply a function value. Then finally, maybe I have another subinterval, and this time, instead of picking the left or right, I'm just going to pick the very middle of it and make that the height of the rectangle. So in which case, it's still a rectangle, it's still base times height for the area, but this time the height is measured in the very center of the subinterval. But regardless of which of these we pick, the general formula for the summation of those rectangles is similar in that the height of each rectangle is a function value, and the width is the distance between 2 successive points. And then the summation simply adds them all together. Well, I'd like to introduce another approach to this today, and that is to use the shape of a trapezoid instead. So let's just take a minute here and see how this sets up for us. I want you to notice that each of the green sections has the similar shape to that trapezoid in the warm-up problem. And I've subdivided my region into about 4 subintervals, and I've numbered the x coordinates of these points, x sub 0, x sub 1, and so on. Now I only have 4 subintervals here, but I'm just going to generally call the last one x sub n. So you notice if I actually had 4 subintervals, the index on this last number is going to correspond to the number of intervals because I'm starting at x sub 0. Now let's imagine we're going to take each of these trapezoids, find their area, and add them together. Well, the first one I would do is notice how wide each of them are. They might all be the same width, but they don't have to be. They could all be different widths. And so each width is computed by taking the distance between successive points. So if I'm on the first subinterval, for example, it would be the x1 minus x0. So I'm going to note here, I would subtract 2 successive points to find the width. Okay. Now the area of a trapezoid is simply that method we showed in the warm-up problem. We need to find the average of these two verticals and multiply by the width. And so let's take any one of them, for example. I would have to take the function values, average them together, and then multiply by the width of that subinterval. And so now I'm just going to generalize this process and work my way through. And so to estimate the total area under the curve, which would be considered the definite integral from a to b, we're simply going to sum together. So the index I starts at 1 and ends at n, which is the number of subintervals. And then the expression in the sum is just exactly that expression that we used up here for the area of the trapezoid. The average of the two function values. So we're going to add them and then divide by 2. Multiply by the width delta x. In the first couple examples, the subintervals and the function values are all going to be provided in a table, and we're simply going to practice constructing this type of sum. In the next video, we'll actually have an exact integral we wish to estimate, and we'll make our own table and solve it this way. So here I have a mystery function f of x, where there's 5 sample values ranging from the x value 0 to the x value 6, and we wish to estimate the definite integral of this function over the interval 0, 6. So we're going to, in using trapezoids, we can picture the graph. This would entirely be in the first quadrant. And what I like to do first is map out how wide each of the trapezoids are. So by noting the x coordinates of those points and by how much that changes each time. I'm just going to make a little note up here. As I go 0 to 1, the width would be 1. From 1 to 3, it would be 2. From 3 to 5, it would also be 2. And from the last one, it would be 1. It's important to make sure you know that not all the widths have to be the same, and I intentionally made this one not the same. So, setting up my trapezoids then, the first trapezoid goes from 0 to 1 on the x scale, and the function values are 1 and 3. So in my first trapezoid, I'm averaging f of 0 and f of 1. And multiplying by the change of x, the width across, which is 1. The second one, I'm going to go from the x value 1 to 3. And average those together, multiplying that by 2. Don't want to forget the width. And then we'll just keep moving on here. F of 3 and f of 5. The width is also 2. And then finally, f of 5 and f of 6. Lastly, the width is 1. So I'm going to pull the numbers from the table, and then we will sum this all together. So I'm averaging 1 and 3. Then 3 and 4. Then 4 and 7. And then 7 and 5. I encourage you right now to maybe pause the video and calculate this grand total on your own. In a minute, I'll write the answer in. And the answer I got here is that this is equal to 26. So the integral from 0 to 6 of this mystery function is approximately equal to 26. We have no guarantee at all of any exact value of this integral because I don't know the expression for f of x. And we found this estimation with the trapezoid method. So for the second one, I would encourage you to pause the video, try to set up this one yourself. In a minute, I will have the solution written out here and you can check your work, but I encourage you to pause the video here and try this one yourself in the same way I just did the last one. So here I have it written out. I have my trapezoid sum written. There were 4 terms. The first one had a jump across of 2, from 0 to 2. Then from 2 to 3, the jump was 1. Then from 3 to 7, the jump was 4. And then from 7 to 8, the jump is 1. And so I'm averaging the function values each time, noting the different widths of the jumps. And I got my grand total to be 33.5. So again, we don't have any guarantee of the exact value of this definite integral, just an approximation method using the trapezoid method. In the next video, we will try this again where we have to make our own table and construct this method this way. We'll see you back on the next video.